All right, so today we're going to talk about the contents of Chapter 10 in the textbook, which consists of information about mass storage systems, primarily hard drives. This is the basic overview of the contents of the chapter. So we're going to look at sort of how disks are structured internally in terms of their hardware. We'll talk just very briefly about how we can attach hard drives or how hard drives are attached to systems. We'll spend a fair amount of time talking about different disk scheduling algorithms. We'll look some at disk management as well as how disks can best support swap space for virtual memory. And we'll kind of finish up talking about RAID structures, redundant arrays of disks. So the basic objectives of the chapter are fairly straightforward. We'll talk about the physical structure of storage devices, secondary devices, hard drives primarily. We'll talk about the performance characteristics. We'll look at the quality of different scheduling algorithms, and we'll look at why we want to use RAIDs if we're really interested in security. Okay, so we'll start with a overview of how hard drives work. So magnetic disks still to this day provide the mainstay for secondary storage in machines. We know that solid state hard drives are coming along, but still magnetic disks provide just by far the largest amount of secondary storage. The standard drive rotates about 60 to 250 times per second. The transfer rate is the rate at which the data can basically move from the hard drive to the computer. The positioning time is how long it takes for the heads to be moved over the data that resides on a hard drive. We'll talk a little bit more in detail about that in a bit. The access time can actually be subdivided into two parts, something called the seek time, which is basically how long it takes for the head to move over the appropriate track or cylinder, and then a rotational latency, which is the amount of time we have to wait on average for the disk to spin so that the data we're actually trying to access is underneath the head drive. A head crash is a very nasty thing, which you hope never happens to you, which is when the disk head actually comes in contact with the spinning disk underneath it, which is usually terminal for the hard drive. Some disks can be removable. That is, you can have a hard drive which you can sort of plug in and out of an array of hard drives. USB drives are removable, for example. Just unplug them from your machine, you can move on with them. And there are several different ways that you can attach hard drives to computers. We'll talk about that in a little bit. So here's sort of a diagram of sort of the internal structure for a hard drive. So over here on the right, you can see a photograph of one. This is one that might be in your PC, for example. The hard drive usually consists of a collection of disks. You can't really see it in this, but there may be 1 to 6 or 7 disks kind of stacked vertically on top of each other. The disks then these platters sit on a spindle, and they spin around that spindle. The area of each disk is then subdivided into a series of concentric rings, which are called tracks. Each of the tracks is then subdivided into a smaller section, which is usually called a block. We want to think about the tracks in terms of how they are stacked on top of each other vertically. So the set of tracks stacked vertically on top of each other is considered to be a cylinder. So you basically have these concentric cylinders of blocks moving along, basically being represented across all the disks. The ARM assembly there is where the head is. So you can see sort of these tong things poking out in the diagram here. So these are the arms, and at the end of each arm is the head, which actually reads the magnetic material as it passes underneath the head. So when you want to access data on a drive, the entire ARM assembly, this whole thing basically moves in or out, which causes all these heads simultaneously to be placed over the tracks that comprise a common cylinder, comprise one cylinder. Then we have to wait for the disk to spin, depending which way it's spinning here, so that the particular block that we want to access, such as this one here, actually passes underneath the head, and then we can actually read the data as it spins underneath. So the size of the platters range from less than an inch to very, very large drives. You don't much have those anymore, the super hard 14-inch giant drives. Most common sizes, if you were to go to like down to Best Buy or something and try to buy a hard drive, you'd basically have 3.5-inch drives, pretty standard for a PC. And then as you get down to laptops, you'll get smaller and smaller drives so that you can fit them in there. Standard capacity for a hard drive these days is, well, if you got a very, very tiny hard drive, it might be as small as 30 gigabytes. Much more commonly now, when you go and buy a hard drive, you're probably getting something like 1 to 4 terabytes. So a great deal of space that you can store on a hard drive compared to how much you can store in the RAM. Theoretically, if you look at the back of a box for a hard drive, they're trying to sell it to you, they're going to say something like the transfer rate is 6 gigabytes per second. If you actually measure the realizable speed, it's going to be much closer to 1 gigabyte per second, or sorry, gigabit per second, which is still very, very fast, but not as fast as the advertisements might say. The seek times, that is how long it takes for basically for the arm to move into position over the track, and then for the rotational latency so that the data we want actually moves onto the hard drive, usually between 3 to 12 milliseconds, an eternity as far as the CPU is concerned, but still, the disk is spinning pretty fast, probably someplace in the neighborhood of 3,000 to 7,200 revolutions per second. The average seek time is got to be calculated based on how long it takes for the seek time to work on basically different tracks and different cylinders, because the seek time is going to vary some depending on which track you're trying to get to, which cylinder you're trying to get to. The latency is primarily going to be based on the spindle speed, that is how fast the disk is spinning. So if the disk is spinning faster, you're going to have less latency. And the average latency is going to be 1/2 the maximum latency, interestingly enough. Okay, so you can see on the table kind of over here on the right-hand side, sort of your spindle speeds and the corresponding latency. It's easy enough to do the calculation. Just take the inverse of this and multiply by 60. So say 1 over 4,200 multiplied by 60 gives you 7.14 millisecond latency. All right, so our total average access time is going to be actually the sum of two different values. You're going to need to add the average seek time, that is how long it takes for the head to get over the appropriate track. And then you're going to have to add in also the average latency, that is how long it's going to take for the drive to spin around so that the block we want is actually underneath the head. And then, of course, there's also going to be a little bit more overhead in terms of having to work with the I/O controller that's built into the hard drive itself. That'll add a little bit extra time. And then we also have to actually transfer the data. So the overall, the average amount of time it's going to take to complete the entire I/O operation working with the hard drive is going to be our access time, plus the controller overhead, plus how much data do we have to transfer divided by how fast we can transfer the data per unit of time. So here's a simple example. Let's say that you wanted to transfer a 4 kilobyte block from a hard drive that happened to have a 7,200 RPM disks spinning with a 5 millisecond average seek time and a 1 gigabit per second transfer rate. And you had a 1/10 of a millisecond controller overhead. So what's our average latency going to be? Well, then you're going to take the speed of the hard drive, 7,200 RPM, take the reciprocal of that, multiply it times 60 seconds per minute, because you want to get rid of this M over here and get to seconds. And then you want to go ahead and take the average. You want to take the average of that, take 1/2 of that, and that's going to give you 4.166 repeating milliseconds. So on average, you're going to have to wait about 4 milliseconds for the drive to rotate around to get to the data you're going to want. So then the overall, using our formula up here, our overall cost is going to be 5 milliseconds. That's our average seek time up here. Then we can add in our latency. That's our 4.17 milliseconds. Then we can look at how much data we want to transfer. So 4 kilobytes per second. Divide that. So here's our 4 kilobyte block. Sorry, divided by our transfer rate, 1 gigabit per second. And then we add our little overhead here for our controller. And so that gives us this calculation down here, resulting in an overall time of about, on average, 9.39 milliseconds to transfer a 4 kilobyte block from the hard drive onto our machine. This, by the way, is a kind of calculation you should be comfortable with by the time you get to the exam. All right, so the first commercial disk drive, I love this picture from the book, shows this gigantic box. So this was 1956. If you purchased an IBM mainframe back in the day, then you'd get this very large hard drive. You can see that it was capable of storing only 5 million characters, and each character represented only with 7 bits, by the way. And the hard drive, you can kind of see it here. This column, this cylinder here is a stack of 50 24-inch platters, pretty darn large platters. And the access time was around about 1 second. So the disks were not spinning all that fast, and the arms weren't moving all that quickly, mostly because the arms had to move across such a large space. 24 inches, that's a 12-inch radius you got to move the arms across. Now, of course, we see that hard drives are being replaced by solid-state disks. The capacity for solid-state disks is still quite a bit less than we find for hard drives, at least on it, and the cost is still quite a bit more expensive per megabyte. So hard drives are going to still be around for a while, but it's probably reasonable to expect, as the price of solid-state drives continues to fall, that one day they may perhaps replace completely regular hard drives as we're used to now. But we'll have to see. They're much faster because there's no rotational latency, there's no seek time. They're not as fast as actual RAM is, and usually because they're plugging into the same kind of hardware that the hard drives would plug into if they were there, the buses that the solid-state drives are plugging into can't actually transfer data as fast as the solid-state drives could actually deliver the data. So that's something which PC manufacturers are working on now. They know they're going to have solid-state drives, so they're changing kind of the bus architecture so that data can be transferred as fast as solid-state drives can provide it, but we're not quite there yet. Of course, one of the big advantages of solid-state drives, no moving parts, so we don't have to worry about vibration and how that might affect the heads on a disks. We don't have any chance of a disk crash or anything like that. We're not really too sure about the lifespan of solid-state disks. There's some talk that the lifespan might not be as long as you might get out of hard drives. We'll have to see. That a lot of it's probably just engineering, trying to keep the solid-state disks cool enough. There is some concern about how many times you can overwrite or change the value of a solid-state disk, and maybe there's a lifetime number of times you can like flip those bits, but we'll find out more about that as the years go on. All right, so magnetic tape was the earliest secondary storage. Before there were hard drives, we had tapes. And I love the picture over there on the right. That's actually a photograph of the very first tape drive. I think it's about 1951, 52, something like that. That was an IBM machine. And originally the tapes are these guys up here in the image. So you have these two wheels over here. So the tape would lie on one wheel and would spool across through these slots down here and then spool back onto the hard drive. So you'd basically go from, you'd spin it off of one wheel and onto the next reel. They were relatively permanent. That is, as long as you kept the tapes in a cool location away from moisture, they would last a very long time. They could hold very large quantities of data. However, the access time would be very slow because it was sequential access. If you wanted to get at a value on this tape, you'd have to move the whole tape, spin it through the head until you got to that portion of the tape where your information was actually kept. So the tape drives are much, much slower than hard drives. Because of this, they're primarily used as backup. If you didn't need to get to the data very often, then this was an okay way to store it, and it basically meant you could move stuff off that you didn't need very often, data that you didn't need very often, off of a hard drive and onto a tape, and only pull it back from a tape onto a hard drive in the rare events when you might need it again. In general, once you actually got to the place on the tape where you needed to access the data, that would be the actual seek time could be huge. But once you're there, the latency, the speed at which the information can be delivered to be about the same as you'd get from a disk. You're just spinning that tape by the head as quickly as you can. Typical storage for tapes was about 200 gigabytes up to 1.5 terabytes. So the density of data on a tape is really to most extent been surpassed now by what we can provide with hard drives. So we're not really seeing magnetic tapes around as much as we did anymore. They are still used for transferring large quantities of data. You're either going to take tapes or you're going to be taking just collections of hard drives. So there may be some, weight and shipping things you have to worry about there. But in general, we don't see magnetic tapes much anymore, but it's good to know about them for their historical reason. Okay, so in terms of how the information on a disk is structured, you basically just want to think about it as a large one-dimensional array of logical blocks, where the block is typically the smallest unit of transfer. Block is typically around 512 bytes. So when you want to access information from a disk, you're going to be pulling it off one block at a time. Low-level formatting of our hard drive is how we create the logical blocks, impose them on the physical media. The one-dimensional array of blocks gets mapped into sectors of the disk sequentially, so the blocks will be numbered. Block 0 will be in the first sector, the first track. Then you have block 2, block 3, so sector 0, sector 1, sector 2. They'll be mapped around like that as you go. So once you've basically filled up all the sectors on one track, then you move into the next track in, and you continue filling out your sectors or blocks as you go around that ring there as well. The mapping of logical blocks to physical sectors is fairly straightforward, unless you have to deal with bad sectors, shown down here. So there's a couple different ways you can deal with bad sectors. Slipping and sparing are talked about in the book a little bit, and we'll maybe get to that a little bit later on. One odd thing about disks is that, of course, the length of a track is going to decrease as you move towards the center of the disk. You just have less circumference. So the number of sectors you can actually store per track is going to vary depending on where the track is located, how far it is from the spindle. And that leads to a little bit of confusion, but I shouldn't say confusion, but complication in determining where sectors are located on a disk. All right, so how do we go about attaching a hard drive to a PC or to a machine? Well, they're usually going to be attached via some kind of an I/O bus, and you'll probably know some of these acronyms. I'm not going to go over them too much, but like IDE and EIDE and ATA and SATA, these have all been around for quite a while now. And of course, we're familiar with USB attachments. Fiber channel is kind of one of the newer protocols for attaching. It provides a very high-speed architecture and is used with high-speed clusters of machines like storage area networks, which we'll talk about a little bit later on. Another old technology is SCSI, SCSI technology. FireWire, that's an Apple approach, and there's actually FireWire 2 now. So there's lots of different ways to attach hard drives to your PC. And they all, they evolve over time as hard drives get faster and faster and the capacity gets larger and larger. The protocols have to adapt to provide more efficiency and higher bandwidth. I already talked about fiber channel. I'm not going to talk too much about SCSI. It's a fairly common attachment protocol. And I'd let you go ahead and read the textbook if you want to find out more details about all of this stuff. It's worth keeping in mind, by the way, again, that the hard drives themselves, each hard drive is going to have its own controller, that's going to be embedded in the hard drive. And so the controller is going to need to communicate with the CPU via the I/O bus or an I/O port and to actually allow the two to interact. Okay, so often these days, disks are clustered together, or they're arranged in an array, a storage array, and the strength of a storage array is that you can have lots and lots of disks that are all kind of working together, and this can provide for RAID technology, which we'll talk about later on. You can provide hot spares, that is, you can have spare drives as part of the array, and when one drive fails, the spare just immediately pops into place and starts working as well, so there's no downtime of the overall array. Or you could have a hot swap system where if a hard drive fails, the system will keep going because the spare, you can basically pull out an existing drive and swap in a new drive, and the system will basically reconstitute the drive you just plugged in, that you swapped in, so that it basically restore the failed drive, the drive that you pulled out. What the information that was there is restored onto the drive that you swapped in. We'll see how we can do that with RAID technology later on, but pretty cool. So The array typically provides for redundancy. You can share your storage across multiple disks. That provides for protection from failure. It can also provide for more efficiency because when you're accessing data, you may be pulling the data instead of from a single drive, you may be pulling the data from multiple drives simultaneously, giving you faster throughput. All right, so a storage area network is shown here. We sort of have our standard network of machines over here of PCs, either a LAN or a WAN. So you got your clients over here on the right-hand side. Maybe the clients are trying to talk to a web content provider or some other kind of a server over here. This is over a normal setup. Now the difference here is we've got another area network. This is our storage area network, and this is a network of secondary or tertiary storage. Like each one of these could be a storage array of perhaps hundreds or thousands of hard drives. And so when our servers need to access data, rather than being plugged directly into a single drive or a set of drives, they instead go through a network to get at the data which may be stored on a storage array or perhaps someplace else. So this provides for a very flexible situation for the servers because somebody else is responsible for kind of maintaining the storage arrays and the storage area network. So the folks who are maintaining the servers can spend their time specializing on the data manipulation stuff, which is kind of what they're supposed to be doing. So typically, in order to realize a storage area network, the hosts are going to be connected directly to the switches that connect the different storage arrays. Switches or routers, so they can move the information quickly back and forth. Almost always, if you're going to have a storage array, you're going to be using fiber channel because the switches need to be super duper fast because you're just trying to move this huge amount of data across a relatively narrow bandwidth. So the fatter we can make that bandwidth, the better. And usually, if it's set up like this, we can use the fiber channel relatively easily. It provides good support for adding and removing extra disks to our storage area networks, and that's a good thing. All right, so for network attached storage, I don't go into this too much detail. The idea here is that rather than having sort of special purpose hardware that supports clusters of disk drives. Instead, this looks much more like a regular network system where we got clients over here, and you have just a standard network over there, and on the other side over here, you have your network storage that's attached. So you may have something like this, in fact, in your own home. If you've got a standalone device, a hard drive, that may have built-in network capability, so you can actually just plug it into your, maybe wirelessly or maybe through Ethernet, you can plug it into a network, and then that hard drive or that cluster of hard drives is accessible to your clients directly over a standard network protocol, so TCP or UDP, something like that. So that'll work, and it's common for situations where you don't have large amounts of data that you have to serve. Okay, so now we're going to move on to talk about disk scheduling. And this is in some sense related to some of the virtual memory algorithms that we looked at previously. But the idea here is that with virtual memory, we had this concept of a number of requests coming in for pages that we needed to access. So disk scheduling similar. A disk may be getting requests from multiple processes, sort of firing in, asking the disk to go ahead. I need, I need the content of block 50, I need the content from block 80, whatever. And so the disk needs to determine in what order to satisfy those requests. The requests are coming in too fast for them to be handled sort of individually. Then the request will kind of pile up in a queue on the disk drive's controller, and so the controller has to decide in what order to respond to the requests that come in. In general, our access time is going to be controlled, as I've kind of pointed out before, and what we're trying to typically do is to minimize how much time it takes to satisfy requests on average. So we've already pointed out that the access time for a hard drive has two major components. We have the seek time, that's how long it takes to actually move the heads over the appropriate cylinder for the block that we want. And then we have the rotational latency, that's how long we have to wait for the disk to spin so that that block is underneath the head. So we're trying to minimize our seek time, and to minimize the seek time, we want to minimize how far we have to move the head. So the idea there is that the head, remember, is moving back and forth towards the spindle and away from the spindle. So if we have to move from one track to the adjacent track, that won't take very long because the head does not have to move very far. But we have to move the head all the way from the outermost track to all the way over the innermost track. The head's got to move over a lot more distance, and that's going to take more time. So what our scheduling algorithm is going to worry about is minimizing that seek time. There's not much we can do to minimize the rotational latency. The disk is just spinning at a fixed rate of speed. We don't have much control over that, but we can minimize the seek time. Our overall bandwidth, we're going to define that as the total number of bytes that we transfer over a unit of time divided by how much time it took from the first request of service upon the completion of the last transfer. That's what we call the bandwidth. Okay, so we want to keep in mind that there's lots of different ways that requests can come to a disk for servicing. So one way they can come is from the operating system itself. So this might be, for example, when we're doing a swap for virtual memory. It could be coming from other system processes that are running, sort of background processes that are running. It could come from the user processes that are running on the system. So all these requests can be floating in at any time. And the requests are going to include information such as, is this an input request? That is, do I want to get information from the hard drive, or is it output? I want to write stuff onto the hard drive. I'll need information like, well, what's the address of the disk? Because there may be multiple disks I'm trying to access. What address am I trying to access in memory? How many sectors do I want to transfer? That kind of thing. So the operating system can maintain a queue of requests that are going to go out to the hard drive. Later on, we're going to see that those queues can also exist on the controller. But for now, let's keep it simple and assume that the entire queue of requests is resident on the operating system. So we'll let the operating system control kind of the order in which the requests are going to go to the hard drives. If a disk is idle, then obviously it can immediately start work on an I/O request. But if the disk is busy servicing a previous request, then the operating system is going to have to queue that request and decide later in what order it wants to provide the requests to the hard drive controller directly. Okay, so we're going to look at a number of algorithms here. Kind of like we did with the virtual memory chapter when we looked at a particular request string. In that case, the string consists of the elements of the request string were page numbers. Here we're going to have, our numbers are going to be actual track numbers. This is what we have control over. So this would be track 37, track 122. We're ignoring the sector values here because we have no control over the latency for the sector. You're just going to have to wait for the sector to spin so that's underneath the head. And we're going to assume, in our case here, that our head is starting at track 53. So this is the order in which the requests are arriving into the operating system. The hard drive is currently sitting over track 53. We're going to assume that our hard drive has only 200 tracks numbered from 0 to 199. So obviously, the simplest algorithm we could use would be first come, first serve. And so that's kind of what this diagram shows here. So you'll start with, you can kind of think about time as running vertically here. So this would be time 0 up at the top, extending time down this way. And we start at track 53. So this is our starting position of the head. And first come, first serve. So the first thing I want to do is move to track 98. So the sloping downward here because time is passing as we move over here, and eventually we get over to track 98. Then from there, the next track to service, the next request is 183, so we move all the way over to 183, and then we move from 183 all the way back to 37 over here, and from 37 to 122, and so on and so forth, going back and forth. Now, the total distance that the arm had to move, that is the amount of, let's start over again. The amount of time it's going to take to service all these requests is going to be proportional to the total distance that the arm had to move back and forth across all of these tracks. So we can calculate that by basically just taking the difference between each of these. So, for example, the number of tracks that this first request took, the first request would be from 53 to 98. So that's this amount up here. So that would be, what, 130. So you get 130 for that. And then to go from 98 to 183 would have that distance, whatever that's supposed to be. And then you'd have the distance go from 183 to 37. So you just basically calculate the differences of all of those things and add them all together. And what you'll find out is that the total distance that the head transferred was 640 cylinders. So that's kind of our starting point for talking about how fast our different algorithms are going to be. 640 cylinders for first come, first serve to satisfy this request string. So the next I'm going to look at is shortest seek time first. And what it does is it looks at the current position of the head, and it looks at all the requests that are pending, and it chooses to resolve the request whose track is closest to the current position of the head. That'll obviously be the shortest seek time because we have to move the head the smallest distance. This is a form of the shortest job first scheduling we looked at in our paging schemes. We have to be careful about this because with shortest seek time first, it is possible that you may get starvation. That is, you may have, if the requests are coming in very quickly, you may have one little lonely request sitting far away from a bunch of other requests. So your whole bunch of processes are running and they're sending in requests, say, for tracks from 1 to 50, and they're all 1 to 50, 1 to 50, on that small range. So the head is constantly moving back and forth. But you have this one pending request, maybe at track 200, and it's always going to be too far to go from the current position to that very distant request. So you can get a starvation situation if that occurs. So if we look at the next slide, we'll use the same reference string, and we'll actually see it's going to turn out where actually the seek time is a lot less. It's 236. But what would we do? If you're going to do this by hand, for example, on an exam, what you're going to want to do probably is to sort the reference string as I've done here. So I took the reference string listed here, and I sorted it out, and I placed the initial head position in the reference string, even though it's not really there, just to kind of point out where you are. So the trick is you're either going to be going left or right. So if you look to the right here, you can say, well, what's the distance there? Well, the distance is 53 to 65 is a distance of 12. And the distance from 53 to 37 is a distance of 16. So 12 is closer. So the first place we're going to go is to 65. So that's going to be this move over here. So that's a movement of 12. Now from here you look. So let's go ahead and cross out the 53 here. That goes away. We'll cross out the 65 because we've solved that. But now we're at the 65. So you're either going to move to the right to go to the 67. You're going to move left to go over to the 37. So if we were going to go to the left, that'd be a distance of 28, which is clearly a lot further than just moving 2 steps to the right. So we'll go ahead and we'll service the 67 next. So we'll go to 67, and that's shown over here. And then from here, from 67, you have 2 choices. You can either go right to the 98, which is a distance of, 31, or you can go from 67 to 37, which is a distance of only 30. So 30 is a little bit closer than 31. So we'll go ahead and shoot down that way and service the 37 next. And then from there, you can either go left to the 14, which would be a distance of 23, or you can go right to the 98, which is a distance of, 61. So the 14 is obviously closer. So we go there and we service the 14. So as you continue this process along, the graph shows you the order in which the requests were serviced. And if you went ahead and calculated the distance the head moved and added it all up, so for example, this was a move of 53 to 65 is 12, so you say 12 plus 2 is 14. Just add up all those distances, and the value that we get was that the distance traversed in total was 236 cylinders, quite a lot better than the 640 cylinders that we had to move when we used the first come, first serve approach. So the next algorithm we'll look at is called scan, and the scan is kind of a cyclical algorithm, it's like an elevator algorithm. Basically, once the head starts moving one way or the other, it's going to keep moving until it gets all the way to the outermost track. And then when it hits there, it's going to kind of bounce back and rotate back all the way across to the other end of the hard drive. And it'll sort of keep moving back and forth, servicing the requests as we get to them. we're going to do an example here, and you're going to see it actually does pretty well. It only takes 208 cylinders to satisfy our reference string that we're working on. So let's take a look at that. So again, if you want to work with this, it's probably going to be easier to sort these first to see which way to go, so you won't miss them. But if you don't have to, you don't want to. So we start at 53, and you have to know which way it's starting. So I would say, for example, I would say the hard drive is moving towards the lower numbered sectors, the lower numbered tracks, or to the higher numbered tracks. In this case, it starts by moving to the lower numbered tracks. So from 53, you'd say, well, what's closest to 53 but less than 53? And that's going to be our 37. So it'll move to the 37 first over here. It's still moving to the left. So what's less than 37 but close to 37? And that's going to be our 14 here. So it'll move to the 14. That's over here. And now remember, with standard scan, it'll just keep going, so it's got to go all the way over to the 0. It's kind of wasted work to go there. Then it's going to flip around when it hits the 0 and move back until it gets to the next request, which was made, which is this 65 request. Then it'll hit the 67 request, and so on. Just keep moving back and forth, servicing all those as you go. Again, you do your standard calculation, count how many tracks the head moved across, and as I pointed out before, turns out that was 208 cylinders. So actually a little bit better than the shortest seek time first happened to be in this case. Now, one of the things which is a little weird about scan is calculating the seek time. See how the seek time varies for tracks at different ends. So if I point out that this hard drive has 200 tracks, consider the track if you're at track 100, so you have a request for a track 100. On average, how long is that going to take for your request to be serviced? Well, in the best case, of course, it'll be basically instantaneous. It's already at the track and you're done. In the worst case, you have to wait. So say your request was for 100. The head happens to be at track 101, is moving to the right to larger values. Then it's going to go all the way to the 200, flip around and come back to the middle. So in the worst case, it's going to take about 100 to go out and then 100 to come back. So the worst case is going to take, trying to draw here, 200. It's going to take 200 in the worst case if you're in the middle to go out and come back. If, however, the request is over on one of the edges, like over here at track 200, again, in the best case, it's going to take 0 because you happen to be on the track where the request is made. But in the worst case, you're going to have to wait for the hard drive, the head to move all the way over here and then all the way back. So the worst case for the requests at the end, at the edges of the hard drive, are going to be 400. Now the average is going to be the difference between the least and the minimum and the maximum of each. So the average for our center request is going to be the amount of time it takes to move 100 tracks, and for the requests on the edges, track 0 and track 200, 199, that average there is going to take about 200 time units to service. So that variance in the seek time can actually make things a little bit complicated for the operating system to try to optimize things. So there's a alternate version of scan called C-scan or circular scan, which provides a more uniform wait time or seek time for requests. And it's basically a simple variant where the head moves from one end of the disk to the other, but when it gets to the other end, it just quickly moves all the way back to the other side, ignoring any requests along the way, and then starts across. So you can kind of think about it like it services requests only moving from, say, left to right, and then it jumps all the way back to the left edge again, and then goes back through and services any requests that came in. So here's a picture of how that might look. Here's our same request string as before. So you'd start at 53. Again, this is going to be easier for you if you sort these on an exam. So from 53, the next request over, and we're assuming we're moving to the right here, will be 65, then the 67, the 98, and so on and so forth. Eventually we get to 183. We have to keep going till we get to the very end. So we go to, it could be, for example, a request comes in as we're sort of moving to the right here between tracks 183 and 199. But eventually we get to the rightmost track, and the head just moves all the way back across, ignoring any request that might be on the way. And then once it gets over here, it starts up back, moving to the right again, servicing any remaining requests that are there. And by the way, this seems like it might be a little weird that we didn't bother servicing requests coming back across. but it turns out that hard drives, if they're going to use this scheme, usually can move, if the head has to move all the way from one track all the way back to the other, it's usually quite fast to do that. There's like special purpose hardware they set up there to make that full move, the full shift from inside to outside or outside to inside very quick. So if you go ahead and do this calculation, you're going to get a slightly different value for the how far the head has moved. I won't bother to do the calculation, but the big advantage of this from the point of view of the operating system, the overall runtime is going to take a little bit longer, but the average seek time for every request is going to be the same, regardless of what track it's for. There's also a look version of both scan and some other algorithms, but the look version for both scan and for cscan, let's call them clook and cscan. And the look version basically, instead of moving all the way to the left edge or all the way to the right edge when the head is moving, will choose only to move as far to the right as the rightmost request that's currently extant, or only as far left as the leftmost request that is currently extant. And so that diagram might look like this. So this is circular look. So it's just like the clook we had before. Sorry, it's just like the cscan we had before. Same thing, but when you get over here to the right, because this is the rightmost request, the head does not continue to move all the way to the right edge, all the way to the maximum track. Instead, once you get to the rightmost pending request, you immediately shoot back across, but instead of going all the way across to the leftmost track, you go only as far as the leftmost or the least numbered pending request, in the case 14. So you can do the same calculation here. Go ahead and calculate how far the head moves in toto. All right, so how do you go about, we've looked at a bunch of algorithms now, how do you decide which disk scheduling algorithm you want to use? Well, shortest seek time first is fairly common. It seems like a pretty good idea. If the disk isn't getting hit with a lot of requests all at once, it actually gives quite good performance. If you're on a system that's getting very heavy load, so lots and lots of requests pouring in, probably not something you have happening on a PC, for example, then both SAN and cscan are going to tend to provide a little bit better performance. Also, you're never going to suffer from starvation, or very unlikely suffer from starvation, and that's a good thing. Again, the overall performance of the system is going to depend on what kind of requests you're getting and how often they're coming in. If you have a relatively low-loaded system, you're probably going to go with the shortest seek time first. But if you have higher a density of requests, then you want to use maybe scan or cscan, or might want to use look if you can have that. So sort of a standard reasonable choice for an algorithm here is going to be either shortest seek time first or look applied either to scan or not. That'll work in most situations. In terms of rotational latency, it's difficult for the operating system to calculate that because the operating system itself is not going to be aware of where the disk is in terms of its rotation. So that's difficult to plug in unless you've got some special purpose hardware to do that. One thing you have to consider is that modern hard drives, a lot of them have in the controller actually have some memory to store pending request. So it may not be the case that the operating system has complete control over the order in which requests are scheduled. It may be something that the controller is taking control of. And in that case, it's going to be much more difficult for the operating system to try to optimize disk usage. You just got to kind of hope that the controller and the hard drive is doing a good job.